Time feels continuous because your body is built to assume. It is. You experience time as a smooth progression because your nervous system depends on continuity to function. Memory forms by linking moments together, creating the impression of duration. This intuition feels reliable, but no physical measurement treats time this way. Atomic clocks do not record a flow. They record transitions. Each second is defined by a discrete oscillation inside a cesium atom. Time, as measured, is already fragmented. The continuity you feel is not observed in nature. It is inferred by biology. Your brain cannot operate on isolated instants. Sensory signals arrive at different speeds. Neural processing takes time. To produce a coherent experience, your nervous system integrates these signals over short intervals, smoothing gaps and overlaps into something that feels continuous. What you call the present is not a moment. It is a constructed window, assembled after the fact from delayed inputs. This window gives the illusion of an unbroken now, even though the underlying signals arrive discretely and asynchronously. This construction is not optional. Without it, perception would fracture. Motion would dissolve into static images. Sound would lose rhythm. Cause and effect would no longer align in a usable way. The sense of continuity is therefore not a feature of time itself. It is a requirement imposed by biological survival. You do not perceive time as it is measured. You perceive time in the only way your nervous system can tolerate. When physics measures time, it does not find a flowing substance. It finds repeated states. An atomic clock counts the number of times an electron changes energy levels. A pendulum clock counts swings. A quartz oscillator counts vibrations. None of these devices detect duration directly. They assume that if a process repeats reliably, counting repetitions can stand in for time. The unit we call a second is not a slice of a flowing medium. It is a convention tied to a specific physical transition. This distinction matters because it reveals a gap between experience and measurement. You feel time moving because your perception depends on ordered change. But physics does not require movement. Equations work the same forward and backward. At fundamental levels, many physical laws do not distinguish between past and future. The sensation of flow has no clear counterpart in the underlying descriptions of reality. Even the word continuous becomes ambiguous under measurement. At sufficiently small scales, time may not divide indefinitely. Some theoretical models suggest minimum intervals, below which the concept of time loses meaning. Whether or not such limits exist, all practical measurement already treats time as a sequence of ticks. Between ticks, nothing is recorded. Continuity is filled in mentally, not observed. This creates an asymmetry. Your experience of time feels dense and extended, but the record of time is sparse. A lifetime contains billions of seconds, yet only a fraction leave any trace. Most moments do not alter matter in lasting ways. They pass without inscription. The universe does not register them. Only your nervous system insists they occurred as part of an unbroken sequence. The reliability of this insistence is deceptive. When conditions change, the illusion weakens. Under anesthesia, time collapses. During trauma, it fragments. In altered states, duration stretches or contracts unpredictably. These distortions do not reflect changes in physical time. They reflect changes in the brain's ability to integrate moments into continuity. Time feels long or short, depending on how memory is formed, not on how many transitions occur. What remains consistent is the mismatch. Physics measures time without flow. Biology experiences flow without measuring time. You live inside the overlap, assuming the two align, because they usually agree well enough to function. But agreement is not identity. The continuity you trust is not guaranteed by the universe. It is generated locally, temporarily, and for a specific purpose. This means that the most basic feature of your temporal experience is not confirmed by observation. The smooth passage you feel has no clear physical analog. Time, as you live it, is not what clocks record. It is what your body must believe in order to persist. Clocks do not measure time passing, only change occurring. A clock does not detect time itself. It counts regular physical changes and assumes they represent duration. Whether it is a swinging pendulum or an atomic transition, the mechanism is the same. If change slows or accelerates, the clock follows it. This means time is never observed directly. What we call time is a comparison between processes. The universe offers no independent signal that time exists on its own. When you look at a clock, you are not observing time. You are observing matter behaving in a repeatable way. The clock face, the digits, or the oscillating signal provide a stable reference. But stability is not the same as duration. The clock does not know whether the universe is changing quickly or slowly. It only knows how many cycles have occurred inside its own mechanism. Time is inferred by comparing that cycle count to other processes, including your own biological rhythms. This dependence becomes clear when clocks disagree. Two identical atomic clocks placed in different conditions will not remain synchronized. A clock on a satellite ticks faster than one on Earth. A clock near a massive object ticks more slowly than one far away. These differences are not malfunctions. They are confirmations that clocks track local physical change, not a universal temporal flow. If time were a background substance moving uniformly, all clocks would agree. They do not. The implication is subtle but strict. There is no master clock outside the universe against which all motion is measured. Each clock carries its own definition of duration, tied to the physics of its environment. When physicists compare clocks, they are comparing histories of change, not sampling an external time stream. Time emerges from the relationships between processes, not from a separate dimension being monitored. This also means that when change ceases, clocks become meaningless. In a hypothetical region where nothing happens, no transitions occur, and no states evolve, no clock could operate. There would be no ticks to count. Whether time exists in such a region cannot be tested, because testing requires change. Time, as defined operationally, vanishes when change vanishes. Your everyday experience obscures this because the world around you is saturated with motion. Atoms vibrate, planets rotate, cells metabolize. Against this constant activity, clock readings feel natural and objective. But remove the activity, and time loses its handle. Without events, duration cannot be distinguished from absence. Even the most precise clocks rely on assumptions. Atomic clocks assume that a particular transition will always take the same form under the same conditions. This assumption is supported by observation, but it is not logically guaranteed. The definition of the second is not discovered. It is chosen. It anchors time to a specific process because that process is reliable, not because it reveals time itself. This choice has consequences. When the environment changes, the mapping between clock ticks and other processes changes as well. High velocities, strong gravitational fields, or extreme energies alter rates of change. Clocks respond by ticking differently. Time does not slow or speed in isolation. What changes is the behavior of matter. Time is a label applied after the fact. This framing removes a common intuition. You may imagine time as something that flows and carries events along. But clocks show no sign of such a carrier. They respond only to local physics. The passage you feel is not something they detect. It is something you project onto their output. What remains unresolved is whether time exists independently of change or whether it is entirely derivative. Physics, as practiced, cannot answer this. It operates by correlating observables. If there is time beyond those correlations, it leaves no trace. Every measurement reduces to a comparison of states. This leaves you with a constraint. Everything you know about time comes from observing change. There is no experiment that isolates time alone. Clocks give you consistency, not substance. They allow coordination, not revelation. Time, as measured, is always already something else. The stability you rely on is therefore conditional. It holds only as long as the processes you compare behave predictably. Beyond that, the concept of time loses precision. The universe does not provide a universal tick. It provides only change, unfolding without reference to how long it feels. The age of the universe is not large in the way you imagine. The universe is measured to be approximately 13.8 billion years old. This number feels enormous, but it is not experienced as duration. It is reconstructed from radiation patterns, expansion rates, and particle behavior. The early universe evolved extremely fast. Most structural changes occurred in fractions of a second. When measured by physical transformation, not by calendar intuition, the universe did almost everything it ever would in a remarkably brief interval. The age of the universe is not read from a clock. It is inferred by matching present observations to physical models. The cooling of background radiation, the ratios of light elements, the large-scale distribution of galaxies, and the rate at which space expands all point back to a common origin. The number 13.8 billion years summarizes these relationships. It does not describe a lived span. It encodes a reconstruction. In the earliest moments, after the universe began expanding, change happened at a pace that has no modern analog. Temperatures were extreme. Particles collided constantly. Fundamental forces separated from one another. Matter, as you know it, did not yet exist. Within tiny fractions of a second, the basic framework of physics settled into forms that would persist for the rest of cosmic history. Compared to this initial interval, everything that followed was slow. Structure emerged quickly, then decelerated. The first protons and neutrons formed almost immediately. Simple nuclei appeared within minutes. After that, the universe spent hundreds of thousands of years cooling enough for atoms to form. In terms of physical novelty, these early phases dominate. They define the rules, limits, and possibilities for everything that comes later. The remaining billions of years unfold within constraints established almost instantly. When you imagine 13.8 billion years, you likely imagine accumulation. More time means more development. But cosmological time does not behave this way. After the first few minutes, the universe entered a long period of relative inactivity. Space expanded. Matter drifted. Energy thinned. The passage of time was marked less by transformation than by waiting. Most of cosmic history is uneventful by physical standards. This creates a misleading intuition. The universe is old, but it is not dense with change. The ratio of time to transformation is heavily skewed. Early on, a second mattered. Later, millions of years passed with little alteration to fundamental structure. The same calendar units are applied to radically different regimes, flattening their differences into a single scale. Even star formation, which feels dramatic, occupies a limited window. The first stars ignited hundreds of millions of years after the beginning. Galaxies assembled. Heavy elements were forged. But this activity peaked and began to decline. The universe today forms stars at a slower rate than in its past. Most stars that will ever exist have already formed. Time continues, but novelty diminishes. This perspective alters what age signifies. The universe is not aged like an organism growing steadily. It is aged like an event that happens quickly and then echoes. The long tail of cosmic time is not filled with creation. It is filled with persistence. Structures formed early and then endured, gradually spreading apart as space expanded. Your own existence occurs near the end of the active phase. You live billions of years after the initial transformations, in a universe that has already decided its basic properties. The apparent vastness of cosmic age does not reflect opportunity. It reflects aftermath. Measurements reinforce this. When cosmologists simulate the universe, they compress early time steps and stretch later ones. Numerical models must resolve rapid early changes with extreme precision, while later epochs require fewer updates. The mathematics itself reflects the uneven distribution of significance across time. What remains unresolved is how to interpret this imbalance. If most meaningful change happened almost immediately, what does duration represent now? Does time still carry weight? Or has it become an empty parameter, tracking expansion without transformation? The universe continues to age, but it does so without urgency. The number 13.8 billion years remains accurate, but it describes a history where almost everything decisive happened quickly, and almost everything else followed passively. The length you imagine is not where the substance lies. The universe's age is vast, but its formative moments were brief. Stars live long, only relative to human lifespans. A star like the Sun is expected to shine for about 10 billion years. This sounds vast, but stellar lifetimes are dictated by mass and fusion rates, not by any universal clock. In cosmological terms, stars ignite late and extinguish quickly. Most of cosmic history occurs either before stars exist or after they are gone. The era illuminated by starlight occupies a narrow band in time. Stellar longevity is often described as if it reflects endurance. In reality, it reflects balance. A star persists only because the inward pull of gravity is precisely countered by the outward pressure of nuclear fusion. When this balance shifts, the star changes state. Its lifetime is not a measure of how long time lasts, but of how long a specific physical configuration can remain stable. This stability depends primarily on mass. Massive stars burn fuel rapidly and live briefly. Smaller stars burn slowly and endure longer. The clock that governs a star's life is internal. It is set by density, temperature, and reaction rates, not by any external temporal reference. Two stars formed at the same cosmic moment can differ in lifetime by orders of magnitude, despite sharing the same surrounding universe. From a human perspective, 10 billion years seems almost infinite. From a cosmological perspective, it is constrained. The first stars did not appear until hundreds of millions of years after the universe began expanding. Before that, there was darkness, no visible light, no fusion. After the last stars burn out, darkness returns. The luminous era is bounded on both sides. This means that starlight, which defines nearly everything you observe in astronomy, is not the default state of the universe. It is a temporary condition. Galaxies glow only because they exist during a specific interval, when stars can form and sustain fusion. Outside that interval, the universe contains matter, energy, and time, but little illumination. Even within the stellar era, activity is uneven. Star formation peaked billions of years ago. Since then, the rate has declined steadily. Gas reservoirs are being depleted. Collisions become less frequent. Each generation of stars leaves behind remnants that do not easily participate in new cycles. The universe is aging not just in time, but in available structure. This decline reframes stellar lifetimes. The Sun's remaining 5 billion years are not part of an ongoing, abundant process. They are part of a tapering phase. Fewer stars will be born in the future than in the past. The universe is moving away from conditions that support long-lived, luminous objects. The end of a star is not marked by time expiring. It is marked by fuel exhaustion. When fusion slows, gravity takes over. The star collapses, expands, or explodes depending on its mass. These outcomes are determined by physical thresholds, not by age. A star does not die because it has existed long enough. It dies because its internal processes can no longer sustain balance. This distinction matters because it highlights how little time itself dictates cosmic events. Stars respond to energy flows, not to duration. Their apparent lifespans are secondary to the processes that govern them. When those processes cease, the star's history ends, regardless of how long it has been burning. After stars are gone, the universe does not stop. It continues expanding. Particles continue decaying. Black holes persist. Time remains, but its markers change. Without stars, the universe loses its most visible clocks. Light becomes scarce. Change becomes harder to observe. Your own sense of time is calibrated by starlight. Days, years, and seasons depend on a star's radiation. The fact that stars endure for billions of years makes your temporal framework seem stable. But that stability is borrowed. It exists only because you live inside a narrow window when stars happen to shine. When that window closes, time will not end, but it will become quieter. The era in which stars define duration is temporary. They live long only when measured against you. Measured against the universe, they pass quickly, leaving most of time unlit. The universe spent most of its history without structure. For hundreds of millions of years after the Big Bang, the universe contained no stars, no galaxies, no planets. Matter existed, but it was diffuse and dark. Structure had not yet formed. After stars die out, a similar darkness returns. Complexity is not the norm. It is a temporary deviation. Your existence occurs entirely inside this deviation. In the earliest universe, matter was almost perfectly uniform. Tiny differences in density existed, but they were minute. Gravity had not yet amplified them into anything recognizable. There were no boundaries, no centers, no objects. Space expanded. Particles moved. Radiation cooled, but nothing assembled. The universe was active without being structured. This absence was not brief. It lasted long enough that, measured by today's standards, it would seem empty of meaning. Hundreds of millions of years passed without a single star igniting. During this time, the laws of physics were already fixed. The constants that govern forces and particles were in place. But the universe had not yet produced anything that could be called a system. Structure requires imbalance. Gravity must overcome expansion locally. Matter must clump rather than disperse. In the early universe, expansion dominated. Density was too evenly spread. The conditions that allow complexity were present in principle, but suppressed in practice. Time passed without differentiation. When the first structures finally formed, they did so slowly and unevenly. Regions slightly denser than average attracted more matter. These regions grew denser still, while surrounding areas became emptier. This feedback process eventually produced the first stars and galaxies. But even then, structure was sparse. Vast volumes of space remained almost unchanged. What you call the universe is shaped by these rare concentrations. Your perception is anchored to islands of matter. Between them lies mostly emptiness. This has always been the case. Even during the height of cosmic structure formation, most of space contained very little. After the era of stars, this imbalance reverses. Fuel runs out, formation slows, existing structures decay or drift apart. The universe does not collapse back into uniformity, but it approaches a state where change produces little new organization. Darkness returns, not as a sudden event, but as a gradual thinning of structure. This means complexity occupies a bounded interval. It is bracketed by two long eras where matter exists without organization. Before structure forms, the universe is simple. After it fades, the universe becomes simple again, though in a different way. In both cases, time continues without producing intricate arrangements. Your existence depends on this middle phase. Chemistry requires stars to forge heavy elements. Biology requires stable environments. Observation requires persistent structures. All of these emerge only after the universe has aged sufficiently, and all disappear once conditions degrade. You are not situated at a typical moment. You are situated during an anomaly. This framing alters how time should be understood. If most of the universe's history lacks structure, then duration alone is not a measure of richness. Billions of years can pass without complexity increasing. Time by itself does not guarantee development. It only allows the possibility. The universe does not progress steadily from simple to complex. It transitions briefly into complexity and then recedes. This pattern is not driven by intent or direction. It follows from thermodynamics expansion, and the availability of free energy. Structure appears when gradients exist and vanishes when they flatten. From this perspective, your assumptions about time inherit a bias. You live during the only era when change produces visible results. You interpret duration through the lens of transformation, because transformation surrounds you. But most of time does not behave this way. Most of time is quiet. What remains unresolved is whether structure is essential to time or incidental. Physics does not require galaxies to exist for equations to operate. Time proceeds regardless of whether anything interesting happens. The universe does not preserve complexity. It tolerates it briefly. You exist entirely within that tolerance. Outside it, time is still there, but there is little to mark it. The structured universe you know is not the default state. It is a temporary deviation, suspended between long stretches where time passes without leaving much behind. Geological time reveals how brief biological stability. Earth is about 4.5 billion years old. Multicellular life has existed for only a fraction of that time. Anatomically modern humans appear in the final moments of Earth's history. If the planet's timeline were compressed into a single day, human civilization would occupy less than a second. This is not metaphor. It is proportional scaling based on radiometric dating. Geological time is reconstructed from physical traces embedded in rock. Isotopic ratios decay at fixed probabilities. Mineral layers accumulate at measurable rates. These processes provide a clock that does not rely on memory or narrative. When these clocks are aligned, they reveal a planet that existed for billions of years before complex life became possible, and that will continue long after it is gone. For most of Earth's history, life was simple. Single-celled organisms dominated for billions of years. They altered the atmosphere, reshaped oceans, and laid biochemical groundwork. But they did so slowly. Complexity did not accelerate. Steadily. It stalled for long periods, constrained by chemistry, energy availability, and environmental stability. Time passed without producing bodies, ecosystems, or behavior recognizable to you. Multicellular life appears abruptly in the geological record. This does not mean it emerged suddenly, but it does mean the conditions allowing it were rare and tightly bounded. Oxygen levels had to rise. Climate had to stabilize within narrow limits. Nutrient cycles had to align. When these factors converged, complexity increased. When they diverged, it collapsed. Mass extinctions punctuate the record, erasing dominant forms repeatedly. These extinctions are not anomalies. They are structural features of Earth's history. Asteroid impacts, volcanic eruptions, and climate shifts reset biological progress multiple times. Stability, when it appears, is provisional. Each interval of complexity is temporary, suspended between disruptions. Time alone does not protect life from erasure. Human emergence sits at the extreme end of this pattern. Anatomically, modern humans appear after most geological processes have already shaped the planet. Continents have formed and drifted. Mountain ranges have risen and eroded. Oceans have opened and closed. The biosphere has been rebuilt several times. Human presence occupies a narrow crest at the end of this long sequence. Civilization compresses this further. Agriculture, writing, and industry unfold in a span so short it barely registers geologically. Entire cultures rise and vanish without leaving durable traces. From the perspective of sedimentation and isotopic decay, these events are nearly invisible. The planet does not record them clearly because they do not persist long enough. This mismatch exposes a tension between lived time and recorded time. You experience history as layered and expansive because memory accumulates. The Earth records history as stratified and discontinuous. Long intervals are compressed into thin layers. Sudden events leave outsized marks. Duration does not correlate with significance. Biological stability depends on narrow environmental ranges. Temperature, atmospheric composition, and ocean chemistry must remain within tight bounds. Outside these bounds, complexity declines. Earth has crossed these thresholds repeatedly. Each time, life adapts or collapses. There is no guarantee that the current interval persists. This places human existence inside a fragile window. Not only is it brief, it is contingent. The conditions that support it are neither ancient nor permanent. They emerged late and may not last long. Geological time does not privilege observers. It records only what endures materially. When you measure time by generations, centuries feel long. When you measure time by rock, they disappear. The same processes that reveal Earth's age also show how little of that age supports complex life. Time is abundant. Habitability is not. What remains unresolved is how to reconcile these scales. You plan, remember, and anticipate within a temporal framework that assumes continuity. The planet's record shows interruption and rarity. Your stability is not embedded in Earth's history. It is balanced on it. Geological time does not suggest progress. It suggests repetition, punctuated by brief departures. Your presence is one of those departures. It occurs late, briefly, and without guarantee of continuation. The planet has existed without you for almost all of its history. That fact is not philosophical. It is measured. Civilization exists within measurement. Error. Recorded human history spans roughly 5,000 years. In cosmological measurements, this duration is smaller than many uncertainties in astronomical data. Entire civilizations rise and disappear inside margins of error. From the universe's perspective, human history is not a chapter. It is statistical noise. Scientific measurements are never exact. Every value carries uncertainty. Distances to galaxies, ages of stars, rates of expansion all include error bars that reflect the limits of observation and instrumentation. These uncertainties are not flaws. They are acknowledgments of scale. When you compare them to the span of recorded history, a disparity appears. The entire timeline of civilization fits inside the uncertainty range of many cosmic quantities. This does not diminish human events in emotional terms. It reframes them physically. When astronomers estimate the age of a distant star cluster, an uncertainty of a few million years is often acceptable. That uncertainty alone exceeds the length of agriculture, writing, industry, and recorded memory combined. Civilizations form and collapse within intervals that physics cannot resolve precisely at large scales. This compression exposes how little imprint civilization leaves on the universe as a whole. Cities rise, monuments are built, technologies spread. But these changes rarely alter planetary or cosmic parameters in measurable ways. From afar, Earth's mass, orbit, and radiation output remain effectively constant. Human activity is submerged beneath thresholds of detection. Even on Earth, the geological record barely registers civilization. A thin layer of altered sediment, traces of synthetic compounds, slight isotopic anomalies. These markers are subtle and fragile. They may persist, but they occupy negligible thickness compared to the layers that represent deep time. Most of Earth's history is preserved in rock strata kilometers thick. Human presence occupies millimeters, if that. Measurement error is not ignorance. It is a recognition that beyond certain scales, details blur. When time spans are short, relative to the phenomena being studied, they merge into noise. This is why cosmology describes epochs in millions or billions of years. Shorter intervals do not affect large-scale outcomes. Your sense of historical momentum conflicts with this. You experience history as dense with cause and effect. Decisions matter. Events cascade. This is true locally. But when integrated over cosmic time, these cascades cancel or dissipate. They do not propagate far enough or long enough to shift global parameters. This does not mean civilization is meaningless. It means it is temporally fine-grained. It operates at resolutions that the universe does not privilege. Physics smooths over such fluctuations. Just as thermal noise averages out in large systems, historical noise averages out in cosmic evolution. The concept of an era loses clarity at this scale. Empires, revolutions, and cultural shifts appear discrete to you because you inhabit them. To the universe, they overlap. Their durations are too short to be distinguished from one another. They blend into a single, brief perturbation. This blending challenges the assumption that history accumulates. You tend to imagine progress as a trajectory extending forward. But from a measurement standpoint, civilization does not extend time. It occupies it briefly and then vanishes. Whether one civilization lasts a century or a millennium changes little when compared to the background scale. Even technological acceleration does not alter this relationship. Faster change compresses history further. More events occur in less time, but the total duration remains short. Complexity increases without extending the window it occupies. The margin of error remains larger than the signal. This perspective also reframes future expectations. If civilization were to persist for tens of thousands of years, it would still register weakly against cosmic uncertainties. Longevity alone does not guarantee significance at scale. Only changes that persist across vast durations alter measurable parameters. What remains unresolved is how to reconcile lived importance with measured insignificance. You plan as if history matters, because it does to you and to those around you. The universe neither confirms nor denies this. It simply integrates over longer intervals. Civilization exists in a narrow temporal band. It is real, intricate, and consequential locally. But in the language of measurement, it is smaller than the noise. The universe does not resolve it as a distinct feature. It passes through, leaving only faint traces, quickly submerged by time. Radioactive decay shows how narrow stability. Windows are atomic nuclei decay at fixed probabilities. These decay rates reveal how quickly matter changes state. Elements necessary for life exist only because certain decay chains progress slowly enough to allow chemical complexity. Change the rates slightly, and stability vanishes. The time window allowing complex matter, is constrained by these physical constants. It is not guaranteed. It is conditional. Radioactive decay is not a process that waits for time to pass. It is a statistical behavior embedded in matter itself. Each unstable nucleus carries a probability of transformation. It may decay now, later, or much later, but the overall rate is fixed. This rate defines as to how long certain forms of matter can persist before changing into something else. These probabilities act as hidden clocks. They govern how long elements remain available in particular forms. Uranium decays into lead. Potassium decays into argon. Carbon-14 decays into nitrogen. These transformations are not influenced by environment, pressure, or temperature in any significant way. They unfold according to internal rules that do not reference the surrounding world. The existence of complex matter depends on these rules being finely balanced. Some elements decay quickly and never accumulate. Others decay so slowly that they effectively remain stable over billions of years. The periodic table is shaped by this balance. Many elements exist only because their decay rates fall within narrow ranges that allow them to persist long enough to participate in chemistry. If decay were slightly faster, heavy elements would disappear before planets could form. If decay were much slower, energy release from radioactive processes would change planetary interiors, atmospheric evolution, and thermal histories. The behavior of matter over time is sensitive to these rates. Stability is not a default condition. It is a negotiated one. Geological processes depend on radioactive decay. The heat-driving plate tectonics comes partly from long-lived radioactive isotopes. Without this heat, Earth's interior would cool more quickly. Magnetic fields would weaken. Atmospheres would erode. Surface conditions would shift. Biological stability would be harder to maintain. Biological processes depend on elemental availability. Life requires a specific inventory of atoms, many of which are produced in stars and persist only because they do not decay too quickly. Carbon, oxygen, nitrogen, phosphorus, and iron must remain stable over long periods. Their persistence is not inevitable. It is the result of decay rates that happen to allow it. These constraints define a temporal window. Complex matter can exist only while decay has not progressed too far and while production has not ceased entirely. This window is not infinite. It opens after certain elements are formed and closes as they decay or become unavailable. Time, in this context, is not open-ended. It is bounded by material transformation. You often think of matter as permanent and time as what changes it. Radioactive decay reverses this intuition. Matter contains time within it. The clock is built into the nucleus. Change is not imposed from outside. It is intrinsic. Stability is a pause, not a baseline. This pause is uneven. Some nuclei persist for fractions of a second. Others persist longer than the current age of the universe. The difference between them is not qualitative. It is probabilistic. A small change in parameters would reorder the table, reshaping which elements exist long enough to matter. From this perspective, the universe does not guarantee enduring structure. It allows it briefly under specific conditions. The elements that support complexity are not favored by time itself. They are permitted by decay rates that happen to fall within narrow margins. Your own body depends on this permission. The atoms that compose you are temporary arrangements of nuclei that will eventually change state. The timescale of that change is long enough to support life, memory, and history, but not permanent. The window is sufficient, not secure. What remains, unresolved, is whether these decay rates could have been different or whether they are fixed by deeper principles. Physics does not yet provide a complete answer. What is clear is that complex matter exists only because change proceeds neither too quickly nor too slowly. The stability you rely on is therefore provisional. It is maintained by probabilities, not guarantees. Time, as expressed through decay, is not a neutral backdrop. It is an active constraint. The universe permits complexity only while its internal clocks run at just the right speed. The past is longer than the future. In observable terms, due to cosmic expansion, much of the universe has already become unobservable. Light from distant regions will never reach you. As time progresses, the observable universe shrinks. Future observers will see less, not more. Most of cosmic history will become inaccessible, not because it ends, but because it recedes beyond causal contact. The universe is expanding, and that expansion is accelerating. Space itself stretches, carrying galaxies away from one another. This motion is not like objects flying through empty space. It is the space between them increasing. As a result, there exists a boundary beyond which events can no longer influence you. Light emitted beyond that boundary will never arrive, no matter how long you wait. This boundary defines the observable universe. It is not a physical edge. It is a limit imposed by expansion and the finite speed of light. Everything you can ever see, measure, or infer directly lies within it. Everything beyond it still exists, but it is causally disconnected. Its future will never intersect with yours. As time passes, this boundary moves inward relative to distant structures. Galaxies that are visible today will eventually fade from view as their light redshifts beyond detection. Over sufficiently long timescales, only the nearest gravitationally bound systems will remain observable. The sky will grow darker and emptier, not because objects disappear, but because information can no longer reach you. This creates a directional asymmetry. The past is rich with accessible information. Light from early epochs continues to arrive. You can observe galaxies as they were billions of years ago. You can reconstruct cosmic history by looking outward. The deeper you look, the further back in time you see. The past accumulates. The future does not behave this way. Information does not accumulate forward. Instead, it thins. There are fewer new regions that will ever come into view. The set of observable events contracts. Future observers inherit less data, not more. Their picture of the universe will be simpler and more incomplete than yours. This reversal challenges a common assumption. You might expect that as time progresses, knowledge increases. Locally, this may be true, but cosmologically, the opposite occurs. The universe hides its own history as it evolves. Expansion erases access to distant regions, sealing off vast portions of space-time permanently. This loss is not subtle. Models predict that in the far future, observers will see only their local group of galaxies. Evidence for the Big Bang itself may become inaccessible. Background radiation will redshift beyond detectability. Expansion will erase the very signals that allowed cosmology to exist as a science. From that future perspective, the universe may appear static and unchanging. Without access to distant galaxies or relic radiation, there would be little observational basis to infer cosmic expansion or a hot, dense origin. The past you can currently observe would no longer be reconstructible. This means you live at a privileged moment observationally, not because the universe is special now, but because information has not yet been fully erased by expansion. The accessible past is longer than the accessible future. More history lies behind your horizon than ahead of it. Time, in this sense, does not open outward. It closes. The set of events that can ever affect you is finite and shrinking. The universe does not preserve its own record indefinitely. It disperses it beyond reach. This has implications for how duration should be understood. The universe may persist indefinitely, but persistence does not imply accessibility. Time can continue without leaving traces that can be observed. The future contains fewer recoverable facts than the past. What remains unresolved is whether this asymmetry is fundamental or contingent. It arises from measured expansion, rates, and known physics, not from philosophical interpretation. If these measurements are correct, then the universe is structured such that understanding diminishes over time. You exist during an interval when the past is still visible and the future has not yet erased it. That interval is not guaranteed to last. The universe does not preserve clarity. It allows it briefly, then removes it by stretching space itself. The past appears long because its light is still arriving. The future appears short because much of it will unfold beyond observation. Time does not simply move forward. It carries information away. Time does not scale linearly across the universe. Relativity shows that time depends on motion and gravity. Clocks on satellites tick faster than clocks on Earth. Near massive objects, time slows measurably. There is no single universal present. Different regions of the universe experience different durations for the same events. The time you experience is local, not global. This effect is not theoretical. It is observed daily. Global positioning system. Satellites must correct for both velocity-induced and gravity-induced time dilation, or their positioning errors would accumulate rapidly. Time does not pass identically everywhere. A second on a mountaintop is slightly longer than a second at sea level. A second on a fast-moving spacecraft is shorter than a second for you at rest. Duration is conditional, tied to the local environment and relative motion. The implications extend far beyond satellites. In strong gravitational fields, such as near neutron stars or black holes, time can stretch dramatically. Processes that appear instantaneous to a distant observer may unfold slowly, or even halt entirely from that observer's perspective. Conversely, a traveler falling into such an object might experience only minutes while years pass elsewhere. Time is not absolute. It is relational. Even in regions where gravity is weak and velocities are small, cumulative differences accumulate over cosmological distances. Light traveling from distant galaxies carries information encoded in events that unfolded billions of years ago. Those events occurred in frames of reference, moving relative to each other. The concept of now at the origin of that light has no unique correspondence to your present moment. There is no universal simultaneity, no global clock ticking in unison across the cosmos. This nonlinearity challenges intuition. You perceive time as smooth, uniform, and universal because your nervous system is confined to a narrow gravitational potential and slow velocities relative to yourself. Over local distances and durations, relativistic effects are imperceptible. But scaled across the universe, the same processes play out over vastly different experienced intervals. Cosmic history is not shared uniformly. It is distributed, layered, and frame-dependent. Even the age of the universe is contextual. The 13.8 billion years measured from Earth represents an interval in our frame of reference. A hypothetical observer near a supermassive black hole would measure a different elapsed duration for the same sequence of events. Time does not have a single value. It varies according to local conditions and relative motion. The numerical age of the cosmos is a construct tied to one observational vantage point, not an intrinsic quantity. Relativity also implies that causality is frame-dependent. Two events separated spatially may appear ordered differently to observers in different frames. What you call cause and effect could be inverted for another observer moving at high velocity or in a different gravitational potential. This does not violate physics, but it shows that temporal order is not absolute. The universe has no single temporal backbone on which all events are strung. Your experience of time is therefore bound to your environment. It is tied to the Earth, to its gravitational field, to the relative motion of your frame. Even as you measure seconds, minutes, or years, you are tracing a path that is unique and local. There is no standard of time that exists independently of observers. Duration is emergent, relational, and conditioned. This insight reframes how events in the universe can be interpreted. Supernovae, galaxy collisions, cosmic microwave background, evolution. Each unfolds over timescales that differ depending on where and how you measure them. What seems ancient or brief is not universal. Time itself is fragmented, a network of locally experienced intervals woven together by light signals. The non-linearity of time also interacts with expansion. Distances between galaxies increase, red-shifting light and stretching observed durations. Events that were brief in their local frames appear longer when measured from Earth. The past you observe is a reconstruction shaped by the relative experience of time across space. Ultimately, your sense of a single flowing present is confined to your local conditions. The universe does not share this present. Every location, every gravitational well, every velocity frame has its own measure of duration. there is no cosmic metronome, no universal clock. Time is local, measured, and experienced differently throughout the vast expanse. The early universe contained more time per second. During inflation and early expansion, physical processes occurred at extreme rates. A single second contained more fundamental change than billions of years do now. When we say the universe is old, we are counting seconds that no longer resemble one another. Time stretches. Its meaning shifts with conditions. In the first fractions of a second after the Big Bang, the universe underwent inflation, a period of exponential expansion. Space itself stretched faster than light could traverse it. During this interval, particles collided, forces separated, and quantum fluctuations imprinted the seeds of future structure. The density of events was extraordinary. What we measure today as 1 second contains orders of magnitude less change than occurred during those primordial instants. Seconds were effectively longer in terms of fundamental activity. Time is not measured in these intervals by experience, because no observer could exist to record them. There was no consciousness, no life, no structure capable of noting duration. What exists instead is change, transitions in fields, particle creation and annihilation, symmetry breaking. The early universe compressed immense evolution into incredibly short intervals, producing conditions that would set the stage for everything that followed. Duration as you understand it does not capture this intensity. Even after inflation ended, the universe continued to evolve at rates beyond modern intuition. Quarks combined into protons and neutrons. Photons decoupled from matter. Simple nuclei formed in nucleosynthesis. Each second involved transformations that today would take millions or billions of years in terms of structural consequence. Early time was dense with activity. Later time is sparse by comparison. This disparity highlights the conditionality of temporal experience. Seconds are not invariant measures of change. They are labels tied to specific processes. In the early universe, the tick of fundamental physics occurred at extreme frequency. Now, in a cooler, less dense universe, the same duration permits relatively little transformation. Time is not uniform. Its operational significance depends on environmental conditions and the processes taking place within it. The consequences for cosmology are profound. When we say the universe is 13.8 billion years old, we imply a sequence of seconds measured in our current frame. Yet those seconds are not equivalent to the seconds of the first microseconds. The metric is convenient, but it obscures the fact that early intervals were effectively longer in terms of physical evolution. Duration and activity are decoupled. A second now is not a second then. This also reframes how you should interpret age. Longevity is not synonymous with complexity or activity. The universe may seem old because many seconds have passed, but much of that time is marked by slow transformation. Early seconds were far richer in structural change. Most of what would become significant, atomic nuclei, stars, galaxies, was seeded in a brief window when time was densely active. What follows is largely the unfolding of patterns established almost immediately. Observationally, this is encoded in the cosmic microwave background and large-scale structure. Fluctuations that imprint galaxy formation occurred within the first few 100,000 years. The early universe left its signatures precisely because its rapid transformations shaped enduring patterns. Later evolution merely elaborates on these foundations. The universe's history is not uniform. It is weighted toward its earliest, most transformative moments. Even today, remnants of this early acceleration exist. High-energy physics experiments attempt to recreate conditions similar to the first fractions of a second, illustrating how intense change was. Seconds in those regimes were equivalent to epochs of consequence. The modern passage of time is tame by comparison, smooth and mostly uneventful. Your own temporal intuition is entirely ill-equipped for this. You perceive a second as a consistent interval, but the universe does not. Time stretches, contracts, and transforms with context. What counts as a second depends on what changes occur within it. Early time was dense. Later time is sparse. The meaning of duration is not fixed. It is a property of the universe itself, shaped by conditions rather than measured uniformly. The age of the universe, as it appears in billions of years, compresses and flattens these differences. It counts seconds equivalently for convenience, but physically, the first second contained more change than the last billion. Time is not simply linear. It expands and contracts with the dynamics of the cosmos. Your experience of duration is local, late, and comparatively inert, set against a background where seconds once carried more reality than we can now observe. Entropy measures direction, not duration. The arrow of time is defined by increasing entropy. Systems move from ordered to disordered states, but entropy does not count seconds. It tracks probability. When entropy increases rapidly, time feels fast. When it increases slowly, time feels long. Duration is not intrinsic. It emerges from statistical behavior. In classical physics, you may imagine time as a uniform river, flowing independently of what happens within it. Entropy challenges that intuition. A gas in a box spreads out until evenly distributed. A cup of coffee cools to room temperature. Stars fuse hydrogen into helium. And black holes evaporate slowly through Hawking radiation. Each of these processes is irreversible. They define a preferred direction, past to future, but they do not measure the interval itself. The clock does not tick. The disorder accumulates. Entropy is fundamentally probabilistic. An ordered state corresponds to a low number of microscopic configurations. A disordered state corresponds to a vastly larger number of possible arrangements. Systems evolve toward disorder simply because it is overwhelmingly more likely. The progression from order to disorder establishes before and after, giving time a direction. But the rate of change is contingent. There is no fixed unit of duration inherent in the process itself. Consider two identical systems. One may relax to equilibrium in milliseconds. The other may require millions of years. Both obey the same statistical rules. The difference lies in tau, energy, and interactions, not in the existence of time itself. Entropy provides a sense of ordering events, not of quantifying them in universal units. The arrow points, but it does not measure distance along its path. Even human perception of duration is entwined with entropy. You experience minutes and hours relative to the accumulation of change in your surroundings and your own nervous system. When events are highly active, time feels compressed. When events are static, it feels dilated. This phenomenology mirrors entropy in action. The perception of time depends on the density of transformations, not on any intrinsic temporal flow. On cosmic scales, the same principle holds. The early universe experienced enormous entropy production in a short span. Radiation and matter interacted intensively. Structures formed and decayed. Fields fluctuated. Seconds then carried far more statistical change than billions of years might now. In contrast, the late universe is dominated by slow expansion and low interaction rates. Entropy still increases, but the pace of structural change has slowed. Duration in the human sense feels long because fewer transitions occur per unit interval. This decoupling of direction from duration undermines the idea of a uniform, objective flow of time. A second is not the same in a dense star-forming region as it is in a near-empty void. Entropy progresses in both cases, but the amount of observable change per second differs dramatically. Time emerges as a relational concept. It is defined by transformations between states, not by a background that ticks evenly. Entropy also limits reconstruction. If information is lost to disorder, events cannot be fully recovered. The past becomes inaccessible. The future is uncertain. Time is experienced locally as sequences of changes, but the absolute measure of elapsed duration becomes ambiguous when the global system evolves inhomogeneously. Seconds may pass, but the amount of physical difference they represent varies. The arrow of time is thus a map of probability. It defines what can happen next and what has happened before. It provides a scaffold for causality, but it does not dictate pace. In regions of rapid interaction, the universe feels younger over a short interval. In regions of slow change, the universe feels older over a long interval. Time stretches or compresses according to entropy gradients. Your experience, your clocks, and your memory are embedded within these gradients. They interpret statistical unfolding as duration. But the duration itself is not fundamental. It is emergent, a consequence of sequences of increasingly probable states. Entropy guarantees that events are ordered, but it does not guarantee that time is uniform, absolute, or directly measurable. In this sense, the universe provides direction without measuring itself. The arrow of time exists, but seconds, minutes, and years are human constructs layered atop statistical unfolding. What you call time passing is the perception of order dissolving into disorder. Duration is an effect, not a primitive. It is contingent on how matter and energy explore the space of possibilities, not on an intrinsic clock embedded in reality. Memory creates the illusion of length. You perceive long time spans because you can remember sequences of events. But memory compresses. Years collapse into moments. From a physical standpoint, memory stores traces, not duration. The sense of a long past is constructed after the fact. The universe does not record time the way you do. Memory is inherently selective. Your brain cannot retain every instant. It records features, patterns, and significant transitions. What you recall as months or years is actually a reconstruction pieced together from discrete snapshots of experience. Each moment you remember may encompass countless microseconds of activity, compressed and interpreted according to relevance and salience. This creates a narrative continuity that does not exist physically. From the standpoint of physics, nothing in matter or energy inherently encodes the passage of time in a continuous way. The universe keeps no diary. Atoms, molecules, and photons evolve according to deterministic or probabilistic laws, but they do not accumulate memory. Your memory, by contrast, encodes correlations between states. These correlations are interpreted as duration, producing the impression of extended intervals. Consider a single neuron firing. The biochemical process is brief, lasting milliseconds. You remember the outcome of repeated patterns of neural activity as a single event, often lasting far longer than the underlying physical transitions. Memory operates by summarizing change, not by counting it second by second. Your sense of past duration is therefore a magnification, constructed after the fact, giving the impression of a continuous and lengthy history. This compression extends beyond individual cognition. Societies record events, history, and achievements in artifacts, writing, and cultural transmission. These traces persist long after the original events have occurred. But even collectively, the records do not stretch time itself. They selectively preserve certain states, discarding countless others. Civilization, like memory, creates the illusion of continuous duration from fragmentary evidence. Memory also introduces uneven weighting. Some events feel long, others short. Traumatic experiences can appear elongated, while routine sequences compress into near nothingness. Duration is subjective because memory is selective. Physically, seconds pass uniformly, but perceived time varies. Your experience of history is therefore distorted, amplified, or attenuated by the capacity and structure of memory itself. On larger scales, memory cannot capture cosmological time. The Earth retains isotopic ratios, rock layers, and fossils as traces of the past. But even these are incomplete. Vast intervals of the planet's history are unrecorded or obscured. The universe itself preserves little of what occurred except through indirect signals. Light from distant galaxies, gravitational waves, or elemental distributions. The physical record is sparse compared to the narrative continuity you construct. The illusion of length is reinforced by reflection. When you reconstruct past events, you interpolate between stored states. A year becomes a story, not a sequence of seconds. You link significant points with causal or emotional connections, ignoring the vast stretches of uneventful time. Your perception of time is therefore an emergent property of memory, not a mirror of physical reality. Memory also imposes order where none exists inherently. You perceive a flowing timeline because you recall events in sequence. In reality, the universe contains no universal present, no global temporal ordering. Different regions experience different durations. Relativity ensures that simultaneity is local, not universal. Memory stitches a coherent past where the cosmos itself maintains only relative change. Even anticipation works similarly. Future planning depends on projected patterns and recalled sequences. Your sense of time stretching forward mirrors your memory of it stretching backward. Both are constructed internally. Physical systems evolve according to dynamics, not narratives. Seconds pass, but the brain translates change into stories, giving rise to the illusion of elongated duration. Ultimately, what feels long is not a property of the universe. It is a product of encoding, recall, and interpretation. Memory amplifies selected transitions into extended spans, producing the impression of a dense and continuous past. The universe itself, by contrast, has no mechanism to measure or preserve duration. It only evolves. Duration is a human projection imposed upon the unfolding of events, not an intrinsic feature of reality. Most moments leave no trace at all. Only certain interactions produce lasting records: fossils, photons, isotopic ratios. Most moments vanish without consequence. The universe does not archive time uniformly. What survives is rare. Your awareness of time is biased toward what leaves evidence, not what actually occurs. The vast majority of physical events leave no durable imprint. Particles collide and scatter, energies shift, interactions unfold, and then vanish from all accessible records. Photons travel in straight lines until absorbed or scattered. Atoms undergo countless vibrations, rotations, and quantum transitions. Yet few of these events create observable, persistent consequences. Time, in its passage, is mostly ephemeral. Even on Earth, most events are irretrievable. A raindrop falls, splashes, and evaporates. Its motion alters nothing beyond the immediate. Winds shift, currents flow, and molecules disperse. These sequences occur, but they leave no lasting trace in the environment. Geological and biological processes selectively preserve only extreme, persistent, or repeated events. The majority of phenomena dissolve into statistical noise. This pattern scales upward. On cosmic scales, stars ignite, burn, and die. But photons from the majority of their processes never reach a detector. Galaxies rotate, merge, and deform. Yet the full detail of every event is lost to the void. Gravitational interactions redistribute matter, but only the largest perturbations, those that influence light paths or create detectable waves, leave observable records. Time flows invisibly, almost unrecorded, except where exceptional processes leave a mark. Even within human history, the majority of occurrences vanish. Millions of decisions, conversations, movements, and interactions are never recorded in writing, memory, or physical alteration. What you perceive as a continuous past is constructed from rare traces that survived, documents, artifacts, or remembered events. These traces give the illusion that time is dense and continuous, when in reality, most moments dissipate without leaving evidence. Entropy accentuates this effect. As systems evolve toward disorder, small-scale fluctuations are erased. A fleeting arrangement of matter is likely to disperse rapidly, leaving no detectable signal. Only large-scale or persistent changes persist long enough to be observed later. This makes your sense of historical continuity dependent not on time itself, but on the survivability of certain events. Duration appears significant because a few durable marks anchor your perception. The selective preservation of events also biases understanding. You infer order and progression from surviving records, but those records are not a representative sample of all events. Time seems orderly and continuous because only the significant, the energetic, or the repeated survives. Vast intervals of quiet, unrecorded change are invisible to you, even though they are numerically dominant. This principle applies to cosmology as well. Observational data comes from what the universe broadcasts outward: photons, gravitational waves, particle fluxes. Most of the processes in the universe produce signals too weak, too brief, or too dispersed to survive the journey. Cosmic history is accessible only through a filtered subset of events. The rest has vanished irretrievably. Even memory and culture are subject to this limitation. Societies preserve stories, monuments, and artifacts selectively. Daily events, ordinary lives, and transient occurrences are lost. Your perception of continuity is shaped by the persistence of what survives. The past appears thick because a narrow set of traces remains visible. The majority of activity is gone. In this sense, time is not evenly recorded. What you experience as a continuum is a reconstruction built upon rare evidence. The universe itself does not care which moments are remembered or observed. Most of reality unfolds and disappears silently, leaving no durable imprint. Your awareness is therefore biased. You perceive a structured sequence of cause and effect because you only encounter evidence that survives, not the countless other events that do not. Duration appears real, continuous, and meaningful. But in the vast majority of cases, moments leave no trace at all. Time is mostly invisible. It passes without documentation, and what you know of it is a tiny, exceptional fraction of all that occurs. The future is structurally thinner than the past. Stars will burn out. Matter will decay. Energy will spread. Fewer interactions will be possible. The future contains less structure to record time with. Duration continues mathematically, but physically it becomes emptier. Time persists without events to mark it. The universe evolves toward thermodynamic equilibrium. High energy structures, dense matter, and concentrated radiation will gradually disperse. Stars, once vibrant engines of nuclear fusion, will exhaust their fuel and collapse into white dwarfs, neutron stars, or black holes. Planetary systems will destabilize over immense timescales, leaving orbits chaotic and bodies isolated. The cosmos will become less structured. Complexity will diminish. Entropy will continue to increase, but in a fundamentally different context. Early and middle eras of the universe contain abundant interactions. Photons scattering, atoms colliding, stars forming and dying, galaxies merging. Each interaction produces records, changes, and measurable consequences. In the far future, these opportunities vanish. Matter will be thinly distributed, interactions rare, and energetic events infrequent. Time will persist, but the universe will lack the scaffolding to mark it. Even radiation will become ineffective as a record. Light emitted by distant objects will be redshifted beyond detectability. Cosmic microwave background radiation, the relic of the Big Bang, will fade as photons stretch into lower energy states. Signals that currently allow observers to reconstruct history will no longer exist. The physical mechanisms that encode the passage of time will themselves recede, leaving an empty framework of mathematical duration without measurable events. From a local perspective, gravitationally bound systems may persist longer. Star clusters, black holes, and residual planets may retain structure for billions or trillions of years. But compared to the total scale of the universe, these remnants are negligible. Most of the cosmos will be a sparse, diffuse expanse where events occur too rarely to provide meaningful markers. Time, though ongoing, will feel inert because physical processes capable of defining intervals will be absent. The thinning of structure also affects causality. With fewer interactions, chains of cause and effect become shorter, localized, and isolated. Large-scale systemic change is no longer possible. Events that once propagated influence across space now have little effect beyond their immediate vicinity. The universe loses its dynamism. Its future is sparse, not in mathematics, but in physical realization. Duration exists in principle, but most of it will be unobservable in practice. This contrasts sharply with the past. The early universe was dense, active, and filled with interactions. Every second contained far more change than an equivalent second now. Processes occurred at extreme rates. Stars formed, merged, and exploded. Galaxies collided. Energy flowed through matter in intense concentrations. The past is structurally rich, leaving a detailed record of evolution. The future, by contrast, will lack this richness. Even life, if it persists, will be confined to narrow islands of complexity within a mostly inert cosmos. Civilization, technology, and memory require matter, energy gradients, and processes that can store information. As the universe thins, these conditions become rare. Without structure to encode change, there will be no durable records of events, no way to experience or measure time as we do today. In this sense, the future is mathematically vast, but physically sparse. Seconds, millennia, and billions of years will continue to pass, but few interactions will occur to mark them. Time will persist as a parameter in equations, but its operational manifestation, the measurable evolution of matter and energy, will contract. Duration becomes empty, not because the universe stops, but because it has little left to do. The thinning is inevitable. Stars cannot maintain fusion indefinitely. Black holes slowly evaporate. Matter decays. The universe approaches a state where events are too rare to be recorded or observed. What you consider future time will be largely unstructured, largely unmarked, and largely inaccessible to any observer. The universe will endure, but its endurance will be measured in empty intervals. Time, as you experience it now, is tied to interaction, structure, and change. The future will persist, but with far less structure to provide those markers. Seconds will elapse, but the cosmos will have fewer events to define them. Time will continue, mathematically infinite, but physically impoverished. The future is not dense like the past. It is thin, quiet, and largely unrecorded. The era of observers is brief and unrepeatable. Observers require energy gradients, complexity, and stability. These conditions are temporary. Before them, there is no observation. After them, there may be none again. Observation itself occupies a narrow slice of cosmic history. Time without observers is fundamentally different from time with them. The existence of observers depends on highly constrained conditions. Stars must shine, producing energy that drives chemical reactions. Planets must maintain stable environments, allowing matter to accumulate into complex structures. Atoms and molecules must persist without decaying too quickly, while energy flows must remain sufficiently concentrated to support sustained processes. These requirements are not guaranteed. They emerge only in rare windows of cosmic history. Life arises in these windows, and consciousness emerges within life. The presence of observers allows events to be recorded, patterns to be interpreted, and sequences to be perceived as extended durations. Memory, awareness, and measurement are all contingent on local complexity. Without observers, time is unmarked. Change occurs, but there is no entity to register it. The universe evolves, but the evolution is unrecorded, unperceived, and indifferent. The brevity of this era is evident in scale. Cosmic history stretches over billions of years, yet observers appear only in the last fraction of that interval. On Earth, life required nearly 4 billion years to reach a state capable of generating conscious observation. Humanity, capable of systematic measurement and reflection, exists only in the final moments of this planetary history. Relative to the universe, the duration of conscious observation is infinitesimal, a narrow slice against the backdrop of time. This brevity is reinforced by fragility. Complex systems are prone to collapse. Environmental shifts, resource depletion, and cosmic hazards threaten persistence. Civilization, and even life itself, may end abruptly. The conditions required for observation are delicate. Their existence is temporary, and there is no reason to expect a repeatable window elsewhere in the universe on the same time scale. Observation is, by its nature, contingent and fleeting. The consequences for understanding time are profound. Time, experienced by observers, is layered with interpretation, measurement, and memory. Seconds, minutes, and years are recorded, counted, and reconstructed. Outside this window, time continues, but there is no mechanism to mark it. Physical evolution proceeds, but the notion of before and after is inaccessible without observation. Duration becomes an emergent property, dependent on the existence of entities capable of registering change. Even the physical records of time are observer-dependent. Fossils, artifacts, written histories, and technological traces require interaction with structured matter. A universe devoid of observers would contain matter and energy evolving under deterministic or probabilistic laws, but no evidence of that evolution would remain interpretable. The universe would be temporally real, but experientially empty. Seconds would pass without context or measurement. The rarity of observers also creates a temporal asymmetry. Most of cosmic history occurs without them. Vast periods precede the emergence of consciousness, and likely far more time will follow once stars burn out and matter decays. Observation is confined to a tiny interval, surrounded by stretches of unperceived events. From the perspective of recorded history, observers may exaggerate their significance, but physically, they occupy a brief, unrepresentative fraction of cosmic time. This narrowness emphasizes contingency. The conditions for observation are not inevitable. Slightly different decay rates, stellar lifetimes, or planetary stability could prevent conscious systems from arising at all. Observation exists because the universe temporarily supports it. Outside this window, time persists, but in a fundamentally different mode. It is unmarked, unexperienced, and largely irrelevant from the perspective of entities capable of interpretation. In this sense, the universe is mostly silent. Observation is an anomaly, a brief interruption in an otherwise unobserved progression of matter and energy. Time with observers is measurable, interpretable, and structured. Time without them is raw, unrecorded, and unstructured. The era of observers is not only brief, it is unrepeatable. It occupies a unique, narrow slice of cosmic history, impossible to extend or reproduce at scale. Duration exists differently within it, defined by perception and memory, whereas outside it, time unfolds silently, indifferently, and without notice. Human timekeeping assumes a stable environment. Calendars, clocks, and schedules depend on regular cycles, planetary rotation, orbital motion, atomic behavior. These are local conditions. They are not guaranteed to persist indefinitely. Timekeeping is a fragile practice dependent on environmental consistency. Your sense of structured time arises from patterns in your immediate surroundings. Days are defined by Earth's rotation, years by its orbit around the sun, and months by the moon's phases. Clocks refine these natural cycles into smaller units, leveraging pendulums, quartz vibrations, or atomic transitions. The apparent regularity of these processes gives the illusion that time itself is consistent. But these measures are conditional. They rely on the persistence of physical and astronomical patterns that are neither universal nor permanent. Planetary rotation, for example, is gradually slowing due to tidal friction. The length of a day increases over geologic timescales. Even now, a modern atomic clock can detect subtle variations in Earth's rotation speed. If you extrapolate far enough into the past or future, the period of a day was significantly different and will continue to change. Similarly, orbital parameters evolve. The Earth's orbit is perturbed by interactions with other planets. The Sun's mass changes slightly through radiation, and gravitational waves subtly alter trajectories. The regularity assumed by calendars is an approximation valid only within limited intervals. Atomic clocks, which define the second in modern timekeeping, are more stable, but they too are not insulated from environmental factors. Variations in electromagnetic fields, temperature, or gravitational potential alter their behavior at detectable levels. Clocks aboard satellites must compensate for relativistic effects, accounting for both velocity and local gravity. Even the most precise human timekeeping systems depend on local conditions remaining sufficiently constant to make comparison meaningful. Change these conditions, and the agreed definition of a second becomes contextual, not absolute. This fragility reveals a deeper truth. Human timekeeping does not measure time itself. It measures repeatable physical processes chosen for their regularity and predictability. The underlying principle, counting cycles, assumes that these cycles will continue indefinitely. It assumes that the sun will rise and set with consistent timing, that the Earth will maintain its spin and orbit, and that atomic transitions will proceed reliably. None of these assumptions is guaranteed by fundamental physics. They are emergent properties of a particular place and epoch in the universe. Timekeeping also depends on structural stability beyond Earth. The cycles we track are embedded within a solar system that itself exists in a galaxy, which in turn is part of an evolving universe. Over billions of years, stellar evolution, galactic mergers, and cosmic expansion alter the environment in ways that make local cycles unrecognizable. Civilizations elsewhere, or observers in distant epochs, may be unable to construct analogous clocks simply because the local patterns they would need no longer exist. Even your memory-based perception of intervals is conditional. You track duration by observing repetitive phenomena, sunrises, seasons, or heartbeats. When these cycles shift, your internal sense of time adjusts unconsciously, revealing how tied human perception is to external regularity. Duration is constructed from the stability of local processes, not directly observed as an independent entity. In the far future, timekeeping, as you understand it, will be increasingly difficult. The sun will exhaust its nuclear fuel. Planetary rotations may become irregular due to stellar perturbations. Residual energy in the universe will diffuse, and isolated regions will lack recurring cycles to define seconds, minutes, or years. The precision you take for granted will vanish. The very act of measuring time will require local conditions that may no longer exist. Thus, human timekeeping is provisional. It is meaningful only as long as specific environmental conditions remain stable enough to support the cycles upon which it depends. What we consider a day, a year, or a second is a local convention, not a universal feature. The fragility of these systems underscores the fact that structured, measurable duration is contingent, not absolute. Duration is only as reliable as the processes that define it. And these processes are temporary features of a universe in constant evolution. Time, in essence, is marked by regularity that exists only in specific places and epochs. The clocks you trust, the calendars you follow, and the schedules you maintain all assume the persistence of patterns that are neither eternal nor universal. Human timekeeping is the practice of embedding duration within a temporarily stable environment. Remove that stability, and the measurement of time becomes an impossible exercise. The seconds you count depend on the survival of local conditions, not on the passage of an independent, invariant temporal flow. The universe does not share your sense of urgency. Events you consider slow or fast are defined by biological constraints. The universe does not prioritize outcomes. Supernovae, galactic collisions, and particle decays occur without reference to experience. Your sense of time's pace is irrelevant to physical processes. The speed at which you perceive events is bounded by your nervous system. Neurons fire at millisecond intervals. Synapses transmit information at finite rates, and your brain integrates signals over tens or hundreds of milliseconds to create the impression of continuity. What feels urgent, instantaneous, or prolonged is constrained by these biological limitations. Outside this framework, the universe operates on scales that dwarf and ignore your perception. A supernova, for instance, unfolds over days to weeks in human observation. Yet the physical processes driving the explosion, nuclear reactions, shockwave propagation, and energy transfer, occur across multiple scales, some so rapid they escape direct measurement, others so slow they persist beyond generations. The apparent pace of the event is a translation into human temporal intuition, not a fundamental property. The universe simply follows the laws of physics. It does not compress or expand events to match perception. Similarly, galaxies collide over hundreds of millions of years. Stars orbit, interact, and merge in ways that are imperceptible in a human lifetime. What you might call slow motion is an artifact of your position in space and time. No cosmic clock accelerates or decelerates to accommodate your consciousness. Duration is relative and context-dependent, determined by local interactions rather than universal concern. Even at the smallest scales, time's pace is indifferent. Particle decays, governed by half-lives, unfold probabilistically. Some nuclei remain stable for billions of years. Others vanish almost instantaneously. The universe does not intend for decays to occur in a time frame you can easily measure. Radioactive transitions happen according to probability distributions, not perception. The scale of physical change is independent of observer expectation. Biological urgency also informs human expectations of causality. You anticipate consequences, react to deadlines, and measure intervals to plan action. Yet the universe imposes no such pressures. Black holes accrete matter over eons. Cosmic radiation diffuses over billions of years. Gravity shapes planetary orbits without regard for the timing of human events. The universe has no mechanism for assigning significance or urgency to processes. It operates purely according to physical laws. Your perception of time's pace is therefore anthropocentric. You equate the number of events observed per unit of subjective duration with the passage of time. A week of human activity is long because your memory encodes many changes. A week in a distant, diffuse nebula where nothing interacts meaningfully might as well be instantaneous in experiential terms, even if the same number of seconds pass. Duration, in the cosmic sense, is decoupled from perception. The disparity between biological and cosmic timescales underscores the illusion of urgency. Energy flows, matter transformations, and structural changes occur without concern for human experience. Light from distant galaxies takes billions of years to reach you. Yet the universe does not wait for you to observe it. Stars form, live, and die on timescales incomprehensible to individual observers. The pace of change is intrinsic to physical conditions, not to consciousness. Even human history is fleeting relative to the cosmos. Civilizations rise and fall, but atomic nuclei, stars, and galaxies persist over intervals far exceeding lifespans, often leaving only traces of their evolution. Your deadlines, schedules, and sense of pressure are insignificant against these vast durations. The universe does not accommodate your attention span. This perspective forces a reassessment of how time is experienced versus how it exists. Urgency, speed, and delay are constructs grounded in biological limitation and immediate context. The universe has no mechanism to align processes with perception. Time unfolds according to laws and probabilities that are indifferent, unconcerned, and temporally unconstrained. You may feel pressure, urgency, or impatience, but these sensations are local, subjective phenomena. Stars do not hurry, particles do not linger, and gravity does not pause. The universe operates independently of awareness, indifferent to deadlines, and entirely unconcerned with the pacing that structures human life. Your sense of temporal importance is a personal artifact, projected onto a cosmos that measures only change and probability, without regard for the human perception of speed. Most of cosmic time is inhospitable to experience. There are long stretches where no complex chemistry can occur. Either the universe is too hot, too diffuse, or too cold. These eras dominate the timeline. The interval that supports life is anomalously short, bounded on both ends by conditions that erase complexity. Immediately after the Big Bang, the universe was a searing plasma of elementary particles. Temperatures were millions to billions of degrees. Matter existed, but no stable atoms could form. Protons, neutrons, and electrons collided incessantly, preventing chemical bonds. Complexity was physically impossible. For hundreds of thousands of years, the universe was opaque, chaotic, and inhospitable. Light itself could not traverse space without interacting constantly with dense matter. Observation, in any conventional sense, could not exist. The flow of events occurred, but it was entirely inaccessible to any observer, and no structure could persist long enough to encode experience. When expansion and cooling finally allowed atoms to form, the universe remained largely inert. Hydrogen and helium gases filled vast voids, too diffuse to collapse into stars immediately. Gravity eventually concentrated matter, triggering star formation, but the intervening period was still inhospitable. No complex chemistry, no stable energy gradients suitable for life, no structures capable of sustaining observation existed. These dark ages encompassed hundreds of millions of years, dwarfing the time span that would later host observers. Duration passed silently and without record. Even after stars ignited, the universe remained mostly uninhabitable. Life emerged only in localized pockets, on planets with precise conditions. Water, chemical diversity, and stable radiation levels were required. These regions were anomalies. Across the majority of space and time, conditions were too extreme. Radiation levels too high near massive stars, matter too sparse in the interstellar medium, temperatures too low in distant voids. The habitable fraction of the universe is tiny, both spatially and temporally. On the other end of cosmic history, after stars exhaust their fuel, conditions again become inhospitable. Galaxies dim, energy disperses, and matter decays. White dwarfs cool, black holes evaporate, and residual particles drift in a thin, diffuse sea. The universe continues to age, but the physical processes that once allowed chemical complexity and information storage vanish. There will be no new observers, no new life, no new memory. Time passes, but it is empty in terms of experiential content. This pattern emphasizes the fragility and rarity of observable experience. The intervals that support life, consciousness, or measurement are minuscule compared to the full span of cosmic time. If the universe's history were compressed into a single calendar year, the portion capable of sustaining complex systems would occupy only the last few seconds. Before and after that narrow window, conditions preclude the persistence of structures capable of registering events. Complexity is not normal. It is exceptional. Even in the current epoch, most of space is inhospitable. Intergalactic voids are extremely diffuse, temperatures near absolute zero, and chemical reactions essentially non-existent. The observable pockets of activity, galaxies, stars, and planetary systems, are anomalies in an otherwise inert and unstructured cosmos. The intervals that contain observers are therefore tiny islands in an ocean of inactivity, both in time and in space. From a temporal perspective, this means that what you consider duration, history, or progress occurs inside an anomalous slice. The universe spends far more time in conditions that cannot host experience than in those that can. The vast majority of cosmic time is silent, unobserved, and structurally simple. Observers, memory, and measurement are all ephemeral perturbations in a backdrop dominated by inhospitable eras. Your perception of a continuous past or ongoing present is embedded entirely within this brief window of hospitable conditions. Beyond it, the universe is indifferent. Physical laws continue to operate. Particles continue to evolve. Entropy continues to increase. But the capacity for experience, awareness, or measurement is absent. Time persists, but it is largely empty of complexity. And your interval of perception is both rare and fleeting within the full scale of cosmic history. The universe is mostly inhospitable to experience. Life, observation, and memory occupy an exceptional, narrow slice of time. For the overwhelming majority of its history, the cosmos evolves without observers, without records, and without the structures necessary to define or perceive duration. What you consider history is a brief anomaly in an otherwise indifferent and unrecorded expanse of time. Measurement itself is temporally local. Every measurement you make happens now, in a specific frame, under specific conditions. You reconstruct the past indirectly and infer the future statistically. Time as a whole is never accessed. It is assembled from fragments observed at different distances and delays. When you observe a star, you are not seeing it as it exists at this instant. The light you detect has traveled for millions or billions of years to reach you. The star you perceive is already in the past. Its current state is inaccessible except through indirect modeling. Every observation is therefore constrained to a temporal slice, fixed by the arrival of signals. You cannot step outside your local moment to witness events in real time across the universe. Measurement is always anchored in now, and now is defined by the frame of the observer. Even nearby phenomena are temporally local. Electromagnetic signals propagate at finite speed. Mechanical processes, chemical reactions, and biological responses all require time to register. Your instruments, no matter how precise, record events after they occur. The data is delayed by interaction and processing. Measurement is inherently retrospective. It captures a consequence rather than the instantaneous occurrence of a process. What you call observation is always a reconstruction, filtered through the temporal constraints of your frame. This localization extends to all forms of measurement. Clocks, calendars, and sensors only report change within a context defined by your environment. A pendulum swings relative to Earth's gravity. An atomic transition occurs within a laboratory shielded from external interference. Satellite-based clocks must correct for relativistic effects of motion and gravity. Each measurement is meaningful only locally. It does not provide a universal, frame-independent account of time. Time itself cannot be extracted from a single observation. Only relationships between events in the same or comparable frames allow you to construct duration. The reconstruction of the past is statistical and inferential. Geological strata, isotopic ratios, cosmic radiation, and stellar light all provide partial, delayed information. You infer histories by comparing signals across space and integrating them into models. The past does not exist as a single accessible continuum. It is assembled from evidence that is fragmentary and separated by distance, decay, and probabilistic uncertainty. Each inferred event is conditioned on assumptions and approximations, producing a version of time that is contingent rather than absolute. Similarly, predictions of the future rely on extrapolations of observed patterns. Physical laws allow you to estimate trajectories, reactions, and outcomes, but the future is never directly observed. It exists only as a statistical projection based on local information. The notion of a universal timeline is a construct of inference, a synthesis of locally observed fragments into a coherent model. Duration is emergent, not fundamental. Temporal localization also applies to human perception. You experience events sequentially because your nervous system encodes and integrates local signals. Your memory compresses intervals into discrete traces. Awareness is confined to a moment of integration, immediately past, and anticipated immediate future. Even subjective continuity is therefore a product of local, sequential reconstruction. Your temporal horizon is limited, yet you interpret events as continuous. Cosmologically, the implication is profound. Observers everywhere exist in local frames. No measurement can access the entire history of the universe simultaneously. Causal structure, relativity, and the finite speed of light impose strict boundaries on what can be known or recorded. Time is experienced and measured only in localized fragments. Attempts to unify these fragments into a global narrative are necessarily approximate and mediated by inference. Even highly precise experiments, such as detecting gravitational waves or observing particle decay, operate within these constraints. Signals are delayed by propagation. Instruments integrate data over intervals, and interpretation relies on correlations across frames. Measurement is temporally anchored, not universal. The now in which observation occurs is unique and unrepeatable for each observer, and it cannot be generalized to the universe as a whole. Every measurement you perform, therefore, is fundamentally local in both space and time. Past and future are reconstructed, inferred, and modeled. Time, as a whole, is never directly experienced or accessed. Duration exists only as an assembly of discrete fragments, collected under specific conditions within specific frames. The universe does not offer a universal ledger. It offers only locally accessible events, and the totality of time emerges from the piecing together of these temporally bound observations. Light travel. Time distorts your picture of history. Looking farther into space means looking further back in time. The universe you observe is layered. Different epochs overlap in your field of view. There is no single cosmic moment you can see. History arrives out of order, stretched across space. When you observe a distant galaxy, the light reaching your eyes or instruments has traveled for millions or billions of years. You are witnessing events that occurred long before the Earth even existed. Simultaneously, nearby stars emit light that reaches you in mere seconds. In one glance, your field of view encompasses events separated by immense intervals of cosmic history. Time is not presented sequentially. It is spatially encoded. The farther away an object is, the older the information it carries. The universe presents history as a composite, not a single timeline. This layering is unavoidable because the speed of light is finite. Even the fastest possible signal cannot convey all regions of space instantaneously. Observers are bound to the local light cone, perceiving events only as they arrive. Light from distant epochs arrives simultaneously with nearby phenomena, folding billions of years into the same visual field. The universe you perceive is not a coherent now. It is a collage, a mosaic of staggered temporal layers projected into your current location. The effect becomes more striking at cosmic scales. When you view a galaxy cluster billions of light years away, the image is from a time when the universe was a fraction of its current age. Simultaneously, interstellar objects within the Milky Way reflect processes that are essentially contemporary. Your instruments cannot disentangle these epochs without modeling, yet your perception integrates them automatically. The result is a spatial superposition of temporal states. What you see is a mixture of past and present, with no uniform reference for when events actually occurred. Even large-scale structures emphasize this non-linearity. Cosmic filaments, voids, and clusters contain matter whose history spans vast intervals. Light from the far side of a filament may be billions of years older than that from the near side. Galaxies, forming at different times, appear juxtaposed. Your observation is an amalgam, presenting a heterogeneous temporal sample in a single spatial frame. Time does not unfold sequentially in your field of view. It is layered, overlapping, and unevenly distributed. This has implications for measurement and interpretation. When cosmologists determine redshifts, distances, or ages, they are reconstructing sequences from layered signals. They must disentangle epochs mathematically, translating spatial observation into temporal inference. There is no single snapshot of the universe. All data is filtered through the finite propagation of information. History does not arrive in order. It is reconstructed after the fact. Observation is always partial, always layered. Relativity further complicates the picture. Different observers, moving relative to one another, experience time differently. Simultaneity is not universal. Two observers, looking at the same galaxy from different velocities or gravitational potentials, will disagree on the moment they are seeing. Even within your own frame, distant light encodes epochs that never coexisted according to a global clock. The universe is fundamentally incapable of offering a single cosmic now. Human intuition struggles with this. We tend to imagine the universe as if it were a movie, played sequentially, scene by scene. But what you see is more like a tapestry woven from threads of differing lengths and colors, each representing an epoch. Events that occurred billions of years apart are projected together in a single view. What appears simultaneous is physically separated by time and space in ways that our minds are not naturally equipped to grasp. Even cosmological maps, which attempt to present the universe in a comprehensible format, must translate these overlapping signals into a model. They impose order on inherently layered information, creating the illusion of a coherent timeline. The raw data, unprocessed, is a superposition of epochs, each arriving according to its own light travel time. The universe, as observed, is a collection of pasts stitched together in the present, never offering a unified moment. In this sense, looking farther into space is inseparable from looking into the past. You cannot escape temporal layering. Every observation is a combination of epochs, an overlay of histories that never coexisted except in your perception. The cosmos you see is an archive arriving out of order, stretched across distances, and indifferent to the sequence you impose. There is no cosmic now, only a continual arrival of fragments, each bearing witness to its own era, overlapping and intersecting in your local frame. The present is not a universal feature. Physics provides no definition of a global now. Simultaneity breaks down across distances. What you call the present is a local alignment of processes. Elsewhere, the same events are ordered differently. The present exists only relative to you. Your intuition treats time as a uniform flow, with a single moment shared across the universe. You assume that the now you experience is the same everywhere else. Observers on distant planets, or even in nearby regions of space, might naturally seem to share your temporal frame. But special relativity demonstrates that this assumption is false. Events that appear simultaneous to you may occur in a different order for an observer moving relative to you, situated in a different gravitational potential. There is no absolute present. Consider two observers in motion relative to one another. If one measures two spatially separated events as occurring simultaneously, the other will generally measure them as occurring at different times. This is not a matter of perception or error. It is a fundamental feature of space-time. The ordering of events depends on the observer's velocity and reference frame. What you label as this moment cannot be extended globally. Each observer experiences a unique alignment of events, a local present. Even within your local frame, gravity affects simultaneity. General relativity shows that clocks tick at different rates in different gravitational potentials. A process near a massive star occurs more slowly relative to a distant observer. Two events that appear coincident in one location are separated in time for another. The present is warped by curvature of space-time, and what you experience as now cannot be universally applied. This localization of the present has implications for causality. Cause and effect are always defined relative to light cones, the limits set by the speed of information transfer. No observer can instantaneously influence or measure events beyond their causal horizon. The universe is partitioned into regions, each with its own operational present, each with its own accessible set of events. The present is always conditional on position and velocity, not a universal backdrop. Human experience amplifies the illusion of a universal now. Your perception integrates signals from nearby processes, sounds, sights, and internal neural events. These are nearly simultaneous on biological timescales, creating the impression of a continuous, global present. Yet this is strictly local. Across space, events unfold in different sequences. Your now is an emergent construct of local alignment, not a feature of the universe. Cosmological observation highlights the disparity. Light from distant galaxies arrives at your location after traveling millions or billions of years. The present state of those galaxies is inaccessible. What you see is their past. A distant observer in motion or in another gravitational field would reconstruct an entirely different alignment of events. Simultaneity is relative. There is no cosmic clock ticking in unison across the universe. Even in extreme cases, where space is nearly empty, the concept of a universal present fails. Quantum phenomena evolve according to probabilistic rules. Entangled particles can appear correlated across vast distances, but these correlations do not define a shared present. They only define relationships between measurements. The global now, if it existed, would require a mechanism to synchronize every event across space-time, a mechanism that physics provides no evidence for. The present is therefore always bounded and local. Every observer constructs it from the alignment of processes within their causal horizon. Outside that horizon, events may be ordered differently, and the notion of now loses meaning. Your present exists only as long as you remain in your frame, and even minor changes in velocity or position alter the alignment. Time, from a universal perspective, is a four-dimensional manifold without a built-in division into past, present, or future. The present is a projection, a local feature arising from the interplay of observation, causality, and reference frame. Elsewhere, the same events may be reordered, delayed, or advanced relative to your measurement. There is no privileged moment, no universal this instant, and no absolute present. It exists only relative to you, and it is inseparable from your local frame of reference. Duration has no preferred scale. Seconds, years, and ages are arbitrary divisions. Physics does not privilege them. At fundamental levels, time may be quantized or emergent. At large scales, it dilates and thins. There is no natural unit that defines how long existence should feel. Human convention imposes familiar units on duration. We measure days by the Earth's rotation, years by its orbit around the Sun, and seconds by atomic oscillations. These units structure experience, organize events, and synchronize activity. But they are context-dependent, contingent on local phenomena, and meaningless outside the environments that produce them. Seconds and years are measures that make sense only because you live on a planet with a specific rotation and orbit. Across the universe, these divisions have no relevance. At microscopic scales, time may behave differently. Quantum mechanics suggests that processes occur in discrete transitions. Particles jump between energy states, decays happen probabilistically, and interactions are quantized. There is no continuous river of time at this level, only sequences of changes. Seconds, minutes, and hours cannot describe these intervals in any meaningful way. What you perceive as smooth flow is an emergent approximation of fundamentally discrete events. Duration, as an intuitive concept, does not exist at the base layer of reality. At cosmological scales, duration is equally relative. Special and general relativity show that time dilates under motion and gravity. A second for someone on Earth is not a second for a traveler near a black hole or moving at relativistic velocity. Clocks disagree, and simultaneity is lost. Stretch time across the universe, and each observer constructs intervals differently. Duration loses universality. There is no preferred scale that applies to all observers simultaneously. What feels long or short is relative, not intrinsic. Even the perception of long spans is misleading. Billions of years for galaxies or stars are experienced differently depending on the processes you consider. 1 billion years may pass while nothing changes meaningfully in diffuse gas, yet the same interval may see dozens of generations of stars ignite and die in a dense region. There is no intrinsic metric of how long time is, only a comparison between processes. Your human intuition of scale is anchored in your lifespan, not in physics. Entropy provides a directional measure, but not a scale. The arrow of time emerges from the statistical likelihood of states, not from an underlying clock. Systems move from low to high entropy, and observers interpret the sequence as a flow of time. Yet the pace of that flow is contingent on physical conditions. Near equilibrium, entropy changes slowly. In the early universe, it changed extraordinarily rapidly. 1 second in the young cosmos contained more fundamental change than billions of seconds today. Duration is therefore contextual, stretched or compressed depending on environment. Even our largest temporal categories, geologic eons, cosmic epochs, are human approximations. The universe does not recognize millennia or ages. The formation of a galaxy, the fusion lifetime of a star, the cooling of a white dwarf, or the decay of matter occur according to physical laws and constants, indifferent to divisions imposed by humans. The labels we assign provide understanding, but they do not dictate reality. Duration exists independently, but only in relation to events, processes, and observers capable of measurement. This lack of a preferred scale also undermines the intuition that time is uniform. Clocks tick, life progresses, and stars evolve, but these are relative frames imposed on a deeper, scale-invariant reality. A second in one frame may correspond to years, centuries, or microseconds elsewhere. Time does not have a natural cadence. It is a flexible, context-dependent measure that only acquires meaning through comparison. Duration is therefore both local and emergent. It arises from the accumulation of events, the alignment of observers, and the measurement of change. There is no universal heartbeat of existence. The universe does not prefer seconds, years, or millennia. What you feel as a lifetime, a century, or an instant is entirely contingent on where you are, what you measure, and which processes you track. Time is real, but its scale is arbitrary, unfixed, and devoid of intrinsic preference. The intervals you experience are constructed, not dictated, and the cosmos imposes no standard for the passage of existence. Your lifetime is short, even by biological standards. Many organisms live for moments. Some live for centuries. None experience cosmic duration. Your lifespan is shaped by evolutionary compromise, not by any universal rhythm. It is neither especially brief nor especially long in absolute terms. It simply fits a narrow niche. Your body is constructed to operate within a specific temporal envelope. Cells divide at predictable rates. Neural networks fire within milliseconds. Metabolic processes proceed on timescales suited to survival and reproduction. These limits define the maximum and minimum duration of experience, constraining perception, learning, and adaptation. You perceive the world as continuous because your physiology integrates signals over these timescales, yet the underlying processes are discrete, bounded, and finite. Your lifetime is merely the interval over which these processes remain functional. Even within biology, your lifespan is unremarkable. Certain trees and marine organisms survive for centuries or millennia. Insects may complete their entire life cycle in days or hours. Microbes reproduce in minutes. Life demonstrates immense variation in temporal scale, but all remain microscopic in comparison to cosmic durations. While your perspective assigns weight to decades, the universe operates on orders of magnitude far beyond this frame. From the perspective of atoms, stars, and galaxies, your existence is almost instantaneous. Your mortality is also contingent on environmental stability. Evolution favors organisms that balance energy expenditure, reproduction, and survival. Lifespan is a compromise, long enough to reproduce, short enough to minimize resource cost. Your decades are not a natural unit of the cosmos. They are a solution to local ecological constraints. The same evolutionary pressures that produce a 70-year human life also yield a mayfly's 24-hour existence and a bristlecone pine's 5-millennium span. Biological time is defined relative to survival, not any universal metric. From a cosmological perspective, your lifetime is vanishingly brief. The universe is approximately 13.8 billion years old. Even Earth's history of 4.5 billion years dwarfs the duration of human civilization. If you scale cosmic history to a single calendar year, your lifetime occupies less than a second. Stars ignite, live, and die. Galaxies form and collide. Matter coalesces and decays, all while a human life passes almost unnoticed. Biological durations are islands in a vast temporal ocean, entirely subordinate to the scales of cosmic processes. Your perception of time further exaggerates subjective significance. Years, decades, and centuries are internally coherent because your memory and awareness operate over these intervals. Yet these scales are local and relative. A single heartbeat, a fleeting emotion, or a minor environmental shift can dominate your perceived duration. But these impressions have no relevance to processes unfolding over millennia, geological epochs, or the evolution of the universe itself. Duration is constructed internally, but it is negligible externally. Even when considering human civilization, the scale remains disproportionate. Recorded history spans roughly 5,000 years, a fraction of Earth's lifespan, and an even smaller fraction of cosmic time. Civilizations rise and fall, yet the planet endures. Stars continue their fusion, and galaxies evolve over billions of years. Your experiences, culture, and achievements occupy only a tiny, local, temporal niche. The length of your life is meaningful only within the framework of organisms with similar constraints, and even there, it is provisional and context-dependent. This brevity underscores contingency. Life exists only in narrow windows of physical and chemical conditions. Evolution has produced observers with limited lifespans precisely because these durations maximize reproductive success under local constraints. There is no universal clock dictating optimal length. Your life is neither long nor short in absolute terms. It is a functional interval, calibrated to local circumstances, entirely unaligned with the rhythms of stars, planets, or galaxies. Your lifetime is therefore fleeting on multiple scales. It is short relative to cosmic durations, typical relative to biological constraints, and provisional relative to environmental contingencies. Duration, in absolute terms, is irrelevant to the universe. What matters is local functionality. Time, as you experience it, is constrained, bounded, and temporary. A narrow niche carved out in an expansive continuum where most of existence passes without observers, without memory, and without reference to your brief interval of awareness. Existence happens inside a vanishing interval. When all measurements are aligned, a pattern emerges. Structure, observation, and experience occupy a thin slice between extremes. Outside it, time continues without complexity. You exist inside an interval so brief it almost does not register. The universe does not slow down for it. It simply passes through. From the moment of the Big Bang to the eventual heat death of the cosmos, the vast majority of time is inhospitable to structure. For hundreds of millions of years after the initial expansion, matter was diffuse, energy was uniform, and no stable atoms or molecules existed. Complexity could not arise. Then, for a brief period, matter cooled, galaxies formed, stars ignited, and planets became chemically diverse. Only within this window could life, observation, and measurement appear. The universe itself operates on timescales so vast that this interval is infinitesimal in comparison, a fleeting anomaly in a largely featureless expanse. Even within this hospitable slice, the duration available for observers is limited. Earth formed roughly 4.5 billion years ago. Yet multicellular life emerged only around 600 million years ago. Humans, anatomically modern in form, have existed for roughly 300,000 years, a fraction of a second when scaled to cosmic history. Recorded civilization spans merely 5,000 years. The interval in which intelligent observers can measure, interpret, and understand the universe is extraordinarily narrow. For nearly the entirety of cosmic time, no being exists to witness, register change. Physical processes further constrain the interval of observation. Stars live for billions of years, but they are far from eternal. Galaxies evolve, collide, and disperse. Matter itself decays over vast timescales. Any structure capable of sustaining observation is temporary. The window in which energy gradients, chemical complexity, and stable matter coexist is a transitory peak in a long timeline dominated by entropy. Observation is therefore rare, conditional, and fragile. The brevity of this interval is highlighted by the fate of the universe. After the last stars exhaust their fuel, matter decays, and black holes evaporate, energy becomes uniformly diffuse. No observers will remain. No records will be created. No measurement can be performed. Time will continue, but without any mechanism to encode, perceive, or differentiate it. Complexity, which defines the interval of existence, is bounded not by duration alone, but by the physical conditions that permit it. Once these conditions disappear, existence in any recognizable form vanishes. From your perspective, the present feels continuous, and the past appears extensive. Yet these perceptions are artifacts of memory and cognition. Time itself, measured in fundamental transitions of particles, expands far beyond what can be experienced. The universe is indifferent to the moments of life and observation. The intervals in which complex observers exist are minuscule compared to the span of change occurring elsewhere, and even during these intervals, duration is perceived, not measured. Even the events you consider significant occupy only a fraction of the interval of observers. Every human action, discovery, and record is embedded within a narrow window. Stars continue to burn, galaxies continue to drift, and background radiation permeates space, regardless of whether you notice. Observation and experience do not influence the passage of time. They occur within its flow, transient and unremarkable to the cosmos. Ultimately, existence is a thin anomaly embedded in an expansive timeline. Complexity, observation, and experience are confined to a vanishing interval, short not only compared to cosmic history, but also relative to the potential duration of stable processes. The universe itself continues indifferently, vast and unchanging on its own scale, while your interval of meaningful experience flickers briefly and disappears. You exist, measure, and perceive in a slice so narrow that the universe does not pause, acknowledge, or slow down. It simply passes through, indifferent to the transient pockets of awareness that emerge and vanish within its eternal progression. Your life, your perception, and your capacity to observe are therefore bounded phenomena. They occur only because local conditions temporarily allow structure, energy gradients, and chemical complexity to coexist. This interval is an exception, not the rule. Outside it, time unfolds without notice, structure dissolves, and the universe continues on, indifferent to the fleeting moments of existence that define your experience. You exist in the vanishing slice where possibility aligns, a transient witness to a vast, indifferent cosmos.